I'm going to use 2-bar magnets, and first of all, I place them with like poles opposite. So, of course, they repel each other. If I put a bit of steel now on the pole of that magnet, I don't change the polarity of it by just doing that. If that was a north pole before, then the outside of the steel will still be a north pole, and so it should still repel the other magnet, shouldn't it? Surprise, surprise. Now, in that condition, both magnets are pulling on the steel outwards. They're trying to split it in half. Let's give them the opportunity to do that by making it a double piece of steel. Now, when I release my fingers, will they in fact succeed in pulling it in half? They do. Now, here's a situation, isn't it? In that condition, they just don't want to know each other. But with only a single piece of steel, both magnets are quite happy to attach themselves to it. I told you permanent magnets were going to be difficult, but believe me, there's worse to follow. Suppose I take an unmagnetized steel ball and an unmagnetized bit of steel. I'm going to put the steel ball on the magnet pole. As I approach it and touch it with the unmagnetized bit, I can always succeed in bringing the ball away with the unmagnetized piece. If I put a bit of cardboard in between magnet and ball to begin with, you can actually see the ball jump away from the magnet.
Hello everyone, I want to explain more about this video. First of all, we begin with 2-bar magnets, placing them with like poles facing each other. For example, north facing north. As expected, they repel each other due to their magnetic fields pushing against one another. Now, if we place a piece of steel on the pole of one magnet, we don't change the magnet's polarity. If the magnet was a north pole, the outer end of the steel will also behave like a north pole, since it becomes magnetically polarized. So theoretically, it should still repel the like pole of the other magnet. But here is a twist. When we placed that single piece of steel between the two magnets, they are both attracted to it, even though they were repelling each other moments before. Why does this happen? Steel acts as a magnetic conductor, offering a path of low reluctance for magnetic field lines. Instead of pushing each other away, both magnets now try to draw magnetic flux through the steel, efficiently using it as a bridge. Each magnet is strongly attracted to the steel, creating a net attraction that overcomes their mutual repulsion. Taking it further, if we replace this single steel piece with a double strip of steel and then allow the magnets to pull on either side, they can actually split it apart, showing how strongly they each want to pull the steel toward themselves. Now, let's introduce a new element, an unmagnetized steel ball. When you bring it near a bar magnet, it naturally sticks to the magnets as the steel becomes temporarily magnetized. But here is surprising observation. If we then bring an unmagnetized steel strip near the steel ball and touch it, the ball detaches from the magnet and instead stick to the steel strips. What's going on? The steel strip provides a more balanced path for magnetic interaction, and the ball is now more influenced by the nearby ferromagnetic material than the magnet itself. The magnetic field flows more easily through the combination of the ball and the steel strip. Peace out.